What does number 1 say? So if you've not handed in your Unit 1 workbook, you're going to do that when? Now. If you would like me, rather than just recycling your Unit 1 answer key, I can reuse it next year if you still have it kicking about. You can just bring that up and put it on my desk right here. A cough drop. Are you going to cough? Like they're literally because I'm sick. Do you just want one because you want like candy? No. Okay. Here. There you go. Okay. Your tests are almost marked, yes? Have you read number 3? Almost means that by tomorrow. Yeah? Like I'm really, really close. But I have 15 left out of the 60 where I have just the 2 pages with the measurements. And those are fast to mark. You know, if I had an extra hour and a half, I could probably do it right now, but I'll have to do it at home. Yes, you sure can. Now, just so you know, I don't mind people asking me about when the test is going to be marked, but when they ask me about it in like a sort of what sounds like a demanding fashion, it makes me go like, grrr, because I literally like spent my time when I was sick on the weekend. What did I do with all my spare time? I marked your tests. It takes hours and hours and hours. How long did it take you to write it? I had to mark 60 of them. Okay, so I don't mind if you ask, just don't sound like, you know, entitled about it because it makes me grumpy. Especially when I'm sick, I get grumpy easier. I will try not to be grumpy, but you know. We're all human, right? So I will just do my best not to be grumpy. Are we good with this? Shall we take a look, carry on a little bit with some of those videos, which might help you understand a little bit more what was happening with the homework, if you didn't understand the homework. Yes? No. Bill Nye is noisy. Noisy and fast. Bill Nye's like this. I like things like this. Hmm? Do you want to borrow one? Is there anyone who did not get a book? You can write in it and then you can like take out the pages. Yeah? Hi. Yeah. If anyone else has an answer key that they'd like to hand in, just bring it on up right now. If it's at home and you want to bring it tomorrow, that's also fine. Thank you. Now, one thing I don't know if I pointed out last day, this is at the top of page 7. At the top of page 7, we had this squiggly hyperactive fly model. Remind your partner what that model is called. It is the quantum mechanical, and I ran out of room, model by Erwin Schrödinger. And you can put the umlaut on the O if you want to, but you don't have to. All right, and lastly, the thing that I forgot to mention last day is there is another name for this model. It is also known as the electron cloud model. Can you guess why it's called the electron cloud? Because it looks like a cloud. Yes? So that's also known as the electron cloud model. And I think also I forgot to point out with your block, I did point it out with block 4, but I forgot with you guys. This is on page 5. Page 5. John Dalton's model is known as this is page 5, billiard ball model. Do you guys know what a billiard ball is? It's like when you play pool. You guys know pool? Playing pool or playing billiards. Yeah? So that's where we got to, and we had gotten, I think in this block, we had gotten to here. We hadn't quite finished this up yet in this block, okay? So we're going to just go to that. Let me find the video. We'll pop there. And everything's just a little bit slow. That's okay, I'm also feeling a little bit slow. Oh, oh, it looks like it's coming up. Oh, hooray. Okay, come on. Oh, there we go. Okay, good. Here we go. So much fun. Maybe I need to start downloading these videos. Come on.
Over a long period of time, it's sketched out a particular design.
Okay.
And whereas Bohr called these circular paths, he called them orbits, Schrödinger called the hyperactive sketch-out shapes, he called them orbitals. Here's a circular orbital too. But electrons didn't only make circles. This is actually a sphere because it's a circle in 3 dimensions. Here is another shape, another type of orbital that electrons could also make. Looks like this, sort of 2 teardrops next to each other. So in the quantum mechanical model, electrons don't orbit the nucleus, they buzz around the atom, sketching out different shapes.
So are we good with that? We've filled in that part on page 7. Is there anything on page 7 that you missed or did not get a chance to fill in? Yes. Just like the bottom left? Okay, so yeah, at the bottom left, let's actually just go ahead because I think that's going to be on our next screen, on our next little thing here.
Now let's focus on the nucleus here. Over the same amount of time, and a little bit later, scientists were discovering the 2 subatomic particles that make up the nucleus. So we can refine this picture a little bit more. In 1919, Ernest Rutherford discovered protons, there they are, and then in 1932, James Chadwick discovered neutrons.
Okay, so in the center of the atom, we have the first particle, which is the proton, and we have the second particle, which is the neutron. And those are together in the what? In the, no, they're not in the orbit's out here. The orbital's out here. These are in the middle. And what's the middle called? The nucleus. So the protons and neutrons together make up the nucleus. What is outside of the nucleus? The electrons. Okay? And we have that orbital which contains the electrons. Who discovered the protons? Ernest Rutherford. Chadwick. And neutrons were discovered by James Chadwick. And this is the same model as before, the quantum mechanical model. See if you can tell your partner what the other name is for the quantum mechanical model. The plum tree model. You got some right words in there, but in this model, this little part outside looks like a cloud, and what's that cloud made of? Electrons. So this model is also called the electron cloud model. Yes. Just going to give you another minute there. If you need to copy anything down, do let me know if there's anything missing. Yes. The protons and neutrons are located in the nucleus of the atom. Absolutely correct. Yes. Yep.
So the really correct view of the quantum mechanical model shows the orbitals being sketched out by the electrons, but then also shows the subatomic particles, protons and neutrons here in the nucleus. Now, this is pretty much how we think about atoms today.
So this is the development of the atom. This was the first model, well, this was the second model. What came before this plum pudding model? The billiard ball model that was really simple, right? It was just a sphere. Which one came next? Well, J.J. Thomson was second. Who was third? Rutherford. Okay, Rutherford. And it's because it's English, you don't know whether that's a Ruth, right? Like Ruth Rutherford. It's actually Rutherford, okay? And then after that came Niels Bohr. What was different about Bohr's model from Rutherford's model? Yeah, so that, not the neutrons, but the, what are these particles? Those are the what? No, not neutrons. Electrons. Okay, so those are the electrons, and they go around on the orbits. And then finally, we came to this one. Now, yes, of course. Did any of you have Ms. Lamb last year? Okay, because I heard she did a lot of work with the atom. Which model did you use a lot of in grade 8? You might have used it in other classes as well. Yes? The Bohr model. Is the Bohr model the most recent, up-to-date, correct model? No. However, you used it last year. You're going to use it this year. You're going to use it in grade 10 and grade 11. The only time you're really going to get into the quantum mechanical model is if you take Chemistry 11 enriched. You might do a tiny bit of it in regular Chem 11. Yes? Why is that so? I'd like you to think about that. Think about what this model is like. We've got this orbital. We have another orbital. So if I have an atom that has a couple of orbitals, I've got this one, right, with the nucleus in the center. I also have the one that's shaped like two what? Teardrops. So that would look like this. And then there would be another one that looks like two teardrops, would have come in and out of the board and into the board. And then there'd be one that goes up and down. And all I've done so far is put in 1, 2, 3, 4, 5, 6, 7, 8 electrons. Why might I prefer to use the Bohr model rather than this? Yes? Because it's much less complicated. It's so much easier to visualize. And actually, it's really useful for a lot of the purposes. You can actually see how many electrons do I have, whereas this is crazy, yes? How many electrons do I have? 8, but you only know that because I just told you, yes? Right? This is just too crazy. So the Bohr model is actually super useful. It's really easy to use when you're looking at how things bond together. Okay, so even though the Bohr model is outdated, it is super useful, which just goes to prove that just because a model is not 100% correct doesn't mean that it's not useful. Okay?
But as scientists learn more and more about atoms, as they do more experiments, they're going to find that this model isn't exactly a perfect representation of what atoms are really like, and they're quite likely to change this and refine it even more. Now, as I said, this quantum mechanical model is like the really accurate way to describe atoms. But the thing is with these orbitals, it can really be kind of a pain sometimes to describe simple things that atoms are doing using electron orbitals. And so a lot of times in these videos, when I talk about atoms, I'm actually going to be sort of using a cross between the very current quantum mechanical model and the sort of outdated Bohr model. Just because for our purposes, a lot of the simple things we're going to be talking about, the Bohr model, it works just fine.
So, you have a question there that you're going to fill in the answer to. Why would we use the less accurate Bohr model very frequently in chemistry when it is not as accurate as the quantum mechanical model? See if you can write a sentence or two that answer that question, and then check with your partner. Yes? Yeah, and think about the next question as well. Okay, see if you can think of when it might be more convenient to use the billiard ball model, which is even less accurate, but Dalton. It's the very first one. Right, one more page, at the bottom of that page, yeah. We might use the Bohr model because it's really easy to see the electrons, to count the electrons. It makes it really easy to show bonding. Now, if you happen to have a second color, can you guys guess what molecule is this? Yes, it is H2O, it is water. So it makes it easy to see your electrons, easy to count your electrons. It's just easy to visualize and work with. So that's why we might choose the Bohr model over the quantum mechanical model. Whoa, what happened there? Now, just before I go on to answer this, tell your partner who is the scientist associated with the billiard ball model, and what does the billiard ball model look like? That's our billiard ball model. Just looks like a sphere. Pretty basic model. It doesn't contain the protons, it doesn't contain the electrons, it doesn't contain the neutrons. Have you seen atoms represented like this before, though? Do you guys remember learning kinetic molecular theory last year? Yeah, and when you had solids, what would you draw a solid like? What would I do for a solid? Just a bunch of circles. And what are those circles? Atoms. Oh, do I need to show all their electrons and everything? No, because I don't need them in this instance. I just need to say that these little guys, because they're a solid, they're just hanging out, jiggling. Sometimes it's really nice to have a very simple model. Yes? Sometimes we don't need to see the electrons. This is a what is wrong with me? Why can't I write? Okay. This is a beautifully simple model. So for example, if I wanted to draw water and I didn't want to draw all those rings and all those electrons, I could just draw an oxygen and I could attach to it two hydrogens. And that's it. And that's a pretty nice little model. And sometimes I wouldn't even put the O's and the H. I might just go like this. And that would make a lovely little water molecule. He's good? Okay. Yeah, I'm not going to move. I'm just going to stop talking at this point. Are we good to move on? Okay, we're going to move on to the next page. Now, one thing I'd like you to notice, what does it say about this page at the top? It says this page is enriched material. So you don't need to know it, okay, unless you want to do the enriched section on quizzes, tests, whatever, okay? However, it's really important in sort of understanding how these models got built and it's really interesting. So we're going to take a look at it anyway, but if you're not going to be worried about it, you can just sort of sit back and enjoy the process, yes, rather than worrying about, memorizing it or really deeply understanding it. Okay, so let's try getting this up and running. So this is on page 9.
In this video, we're going to talk about how J.J. Thomson discovered the electron in 1897 using a cathode ray tube experiment.
We're just going to pause until we can make this bigger. Yeah?
We think about atoms kind of like this. They're made up of a variety of smaller subatomic particles. But in the late 1800s, it was all...
Okay, why is it not going big? Yes. There we go.
All about John Dalton's model of the atom. In the early 1800s, John Dalton had proposed that all matter, all stuff, was made up of tiny, indivisible particles called atoms. At first, not many people believed him. But throughout the course of the 1800s, more and more scientists got on board with his idea. But it remained an open question whether the atoms were really indivisible. Were they like tiny little billiard balls, hard and solid? Or were they made of smaller things? No one really knew the answer to that. But J.J. Thomson was able to answer part of that question when he discovered the electron. He discovered that it was much smaller than atoms. He discovered that atoms had electrons. And so he was able to say for the first time that atoms weren't totally solid and indivisible, but they were made up of smaller, subatomic particles. Let's look at how he discovered the electron. So Thomson used what's called a cathode ray tube. It's a big tube of glass that's kind of like a bottle. You can imagine sort of like this soda bottle. It's sealed all over, and then you pump all the air out of it. Okay? And it has these two pieces of metal at this end. So Thomson connected these two pieces of metal to a power source. And here's what happened. A ray shot from this piece of metal across the tube and created a glowing spot over here when it hit a special coating on the inside of the glass.
Okay, I'm just going to pause it there for a moment so you can fill in the box at the top there, the cathode ray tube experiment, discovery of the electron. It was done by who and co-workers? J.J. Thomson, and you can leave out that P if you want to be more correct in the spelling. Thomson, not Thompson. But if you don't care, you can put the P in. Doesn't matter to me. And you can fill in the little box. Down on the bottom diagram here, we have our power source. Here we have our cathode ray. Do you remember what these are made of? They're made of metal. So if you would like to label them, you can. Those are made of metal. Metal. You don't have to label it, but. And you can also fill in on the second diagram on the right, the cathode ray and the power source, because it's going to be the same as before. And now he's going to do some experiments with this cathode ray.
Now, Thomson didn't know what was going on, but what really was going on is that electrons from this piece of metal were shooting out. They were attracted to this piece of metal, which has an opposite charge, but they were moving so fast that they shot all the way across the length of the tube.
Okay, so what's that green thing made of? Electrons. So what is a cathode ray made of? Electrons. The cathode ray is it's a beam of electrons. Okay? Cathode ray is a beam of electrons. Cathode ray is a beam of electrons.
Anyway, Thomson sees this ray and he gets curious as to what it's made of. And so he asks the question, the stuff that the cathode ray is made of, does it have an electrical charge? And here's how he attempts to answer that question. He takes two metal plates and puts them on either side of the cathode ray tube. And then he turns on electricity.
So these are like attached to something, like he didn't put the attachment. This would be attached to another power source somewhere outside of the picture. You just can't see it. But it makes this metal plate positive and this metal plate negative. And just before we go on, let's make sure that we know the following basic facts. What does positive do to negative? It attracts. What does positive do to positive? Yep, yep. It repels. And if you don't know what repels means, it means it pushes apart. Have you ever taken two magnets and put them like North Pole to North Pole and tried to push them together? And what happens? Like, you can't get them together because what are they doing to one another? They are repelling. But if you flip it the other way around, so you have a North Pole and a South Pole, those two magnets will do what? They'll go and they'll stick together because they are attracting. So positive repels positive. What does negative do to negative? Well, repels. So I'd like you to think, and I'd like you to predict what is going to happen to this beam when it sees that positive plate there. Remember, the beam is made of what? Electrons. What charge are electrons? Negative. So we've got this negative beam, and it sees this positive plate. What's going to happen? It's going to attract to it. This negative beam sees this negative plate. What's going to happen to it? It's going to repel. So this beam, instead of going straight, is going to now bend upward towards the positive and away from the negative. It's a beautiful little experiment.
Which makes the top plate positively charged and the bottom plate negatively charged. And check out what happens to the cathode ray. When he turns on the power, he sees that now instead of going straight through, the cathode ray bends up. It bends up towards the positively charged plate. So based on this, he reasons that the cathode ray must be made of stuff that's negatively charged, since it's attracted to the positively charged piece of metal, and he knows that opposite charges attract. But just because he wants to be very careful, he's a very careful guy, he tries to check this another way. So he uses a magnet. If something has an electrical charge and it's moving, a magnet will push it in particular directions.
There is interaction between a charge which is moving and a magnet. So you will get attractive and repulsive forces on a moving charge, not a still charge, but on a moving charge. If you're interested in that, take Physics 12, okay? So these electrons are moving from the left to the right. And so those are moving, and so these magnets are going to have an effect on that iron. Okay. Quantum physics in high school, you got a little bit in. You definitely got some in Chem 11 enriched. You definitely got some in AP Physics 1. And I don't know about the regular physics 11 and 12 year that fits. I know that they did it in grade 12 when I was in school, but that was like 35 years ago. So that's outdated. So it'll probably be in physics 11 or 12 somewhere, the quantum mechanics part. Okay?
So he takes a cathode ray tube, if you want to think that this marker is kind of the cathode ray tube, and he surrounds it with a magnet, just like this. We can kind of show what goes on by slipping the magnet under like this. So anyway, he puts the magnet here, and he sees now that the cathode ray bends in the other direction. It now moves downward. Now, if the cathode ray is indeed negatively charged, this is exactly how he would expect it to move in the presence of a magnet.
Because he knows all about the physics of how the charged particles respond to magnets, okay? You're not expected to know that. He knows that. Isn't that great? Okay?
So this is just further confirmation that whatever makes up the cathode ray probably is negatively charged. So he takes the data that he gets from these experiments, and he's able to draw a few important conclusions about cathode rays and what makes up atoms. Okay, so based on the outcomes of the experiments with the charged plates and the magnet, Thomson is able to conclude that cathode rays must be made of stuff that is negatively charged.
If you wanted to write that down, you could write that down. Cathode rays must be made of stuff that is negatively charged. You could write that under that diagram. I feel like I'm missing a page. I think there's a page missing here, but I don't know. Yes, sure thing.
Okay. He combines the information that he got from the experiments that I just told you about with some other data that he collected. And he's able to come to the conclusion that the particles that make up cathode rays are 1,000 times smaller than a hydrogen atom. Hydrogen atoms are the smallest atoms. So
particles that make up cathode rays are 1,000 times smaller than the hydrogen atom. That tells us, is the billiard ball model correct? Is that it? No, there's smaller things. And he didn't discover this 1,000 times smaller business from the cathode ray tube experiment. That was from some other experiments that are a little bit more complicated, so we're not going to go into those.
This thing that's in the cathode rays must be really, really tiny compared to an atom. And finally, Thomson swaps out the type of metal that's in the cathode tube. He uses a variety of different types of metal, but he finds that all of the different metals he uses give off the same cathode rays, and regardless of what metal he uses, the size of the things that are in the cathode rays is exactly the same. So based on these three conclusions,
So all the different metals give off cathode rays. All of the things in the cathode rays are the same size. That means that all atoms must contain negative things that are way smaller than the atom. Yes? And then they had to give them a name, and so they named them electrons. He didn't know that they were electrons when he started. He was just like, there must be these things, and they must be negative, and I did some other experiments, and I know they're all smaller than the atom, and they come out of every single metal. I can put copper here, and I get a cathode ray. I can put aluminum here, and I get a cathode ray. I can put gold here, that's an expensive one, and you get a cathode ray. So all the different atoms have to contain those particles. And remember, this actual experiment itself is enriched stuff, so if you don't actually understand the entire experiment, don't stress about it, okay?
He's able to come up with the idea that atoms have tiny, negatively charged particles inside them, and these things that we're talking about here are electrons. Now, if you're like me when I first learned this, you might be confused how these conclusions definitely tell him that there are electrons inside atoms.
I'm just going to pause that, so if you want to write what's in the little box there, you can do so. It's your choice whether you do that or not. Oh my God.
I remember when I first learned this stuff, I was thinking like, wait, doesn't this just show that electricity or cathode rays have negatively charged stuff? How does this tell us anything about the atoms? Okay, here's why. At the time that Thomson does this experiment, everyone, for the most part, agrees that all things are made up of atoms, that atoms are the smallest things that make everything up. They're like the smallest things in the universe. So if Thomson is able to show that there are even tinier things, well, where are those tiny things coming from? They have to be coming from atoms because everything's made of atoms, right? That's the only place they can be coming from. And even if electricity, even if you want to say, well, he's just showing that electricity is made of electrons, well then, still, where are the electrons coming from that make the electricity? The electrons have to be coming from other atoms. And since he can move or remove these pieces of metal and swap other metals in, and he still gets electrons, it again shows that all different types of atoms are able to release or give off electrons. So they must be in there to begin with. Anyway, these conclusions that Thomson comes to have dramatic effects on how scientists think about what the atom actually looks like. Now, at the beginning of the video, we said that in Dalton's atomic model, atoms are indivisible, that they're not made of anything smaller. But when Thomson discovered that atoms have tiny negatively charged electrons inside them, he essentially disproved this model, at least the part about the indivisible atoms.
So what did his model look like? Tell your partner. Maybe draw yourself a little picture. What did Thomson's model look like? See, See if you can draw Thomson's model anywhere on that page you want to. And everybody needs to be able to draw Thomson's model. Yeah, sure thing.
So here is the model of the atom that Thomson comes up with. He realizes, first of all, that electrons are negative. We already talked about that. But then he notices that on the whole, atoms in general are usually electrically neutral. So even though they have these negatively charged electrons inside them, the atoms as a whole don't have a charge. So Thomson realizes that in order for the atoms not to have a charge, there must be some positive charge in the atom that can balance out the negative charge of the electrons. And then the positive and the negative balance out, and the atom as a whole doesn't have a charge. So he comes up with a model that he calls the plum pudding atom. Now, plum pudding is kind of a British thing, so if you're American, it might be better for you to think about this as like the blueberry muffin model. And here's how it works. Thomson imagines that the atom is like a blueberry muffin, and that electrons are stuck in this atom the way blueberries are stuck in a blueberry muffin. So you have these little electrons that are stuck in the atom, but then they're surrounded sort of by a dough. And the dough, like in a blueberry muffin, keeps these electrons or blueberries held in place, but the dough itself has a positive charge. And it's that positively charged dough that is what balances out the negative charge of the electrons. And so together, they don't have any total net charge. So the atom is electrically neutral. So that's how J.J. Thomson's discovery of the electrons leads to this plum pudding model. But now J.J. Thomson didn't have it quite right, because it turns out that the positive charge in the atom isn't sort of spread out in this dough pudding, but instead it's concentrated right in the center of the atom, where the nucleus is. So that's going to be the next step in discovering what the atom really looks like, if you're interested in how scientists
Okay, and we're going to look at that one next day. For today, though, we are actually going to take a look at a plum pudding, because you keep hearing about this plum pudding model and you're told, yeah, it can be like a blueberry muffin, but I think it's super fun. You may not agree with me. I don't know. We'll find out. I think it's super fun to know what a plum pudding is. Yes. Yes, you can. You're going to miss the plum pudding, though. Just letting you know. Okay. And, oh, did I not link it here? Dang it. Okay, so I need to open 2.1b and get the link. Maybe even, let's see if I can just find it. Flaming plum pudding. Yeah, this is the one. Okay, I'm going to turn down the lights so you can see it. Now, the interesting thing about plum pudding, does it contain any plums? No, there are no plums in plum pudding. Back in Victorian times, the word plum, what did the word plum mean? Does anyone know? It just meant dried fruit. Plum meant dried fruit. So really, a Christmas pudding, the plum pudding, just contains a lot of, he's Australian, I think, actually.
We're going to be taking...
So it really contains just a lot of raisins. I'm going to make this bigger so that we can see it, and then we're going to watch this. Okay, here we go.
Hi, and a big welcome to Steve's Kitchen. I've got the Christmas hat on again. One of my subscribers, or one of the viewers here, Bread Sandwich. Now, they had a different name earlier in the year. They've changed it to Bread Sandwich. Well, it's a great name. They asked me whether or not I could show them how to flame a Christmas pudding the way we do it at Christmas. And I promised for quite some time that I would do this. So I'm going to take one of last year's Christmas puddings, this beauty here, and I'm going to flame it. We're going to be taking...
And if you're wondering why it's last year's, it's because part of the process of making a Christmas pudding is to pour rum or brandy all over it and then let the alcohol evaporate. And then you pour more on and then you let it evaporate. So by the time you're finished, it takes on the flavor of the brandy, but the alcohol, it has a very low alcohol content because the alcohol all evaporates off. But you do this final step where you actually pour flaming liquor all over and it burns. So there's actually very little alcohol left from that either.
We're going to be taking some brandy. I'm going to be pouring a shot of brandy into a ladle, heating it up over a candle, and then we're pouring it over the pudding. Let me show you how it's done. Now picture this, if you will. It's Christmas Day. It's been beautiful. It isn't September. It isn't sunny outside. But it's actually Christmas Day. We've just had the family around. We've had the big Christmas turkey and the beautiful ham. And now everybody's feeling really overfull. And then you bring the Christmas pudding out. And everybody knows there's just enough space. So we get our brandy on the ladle. We've got a candle on the table. If you haven't got a candle, you can always do this over the gas stove. And we're just going to heat that brandy through. As the brandy heats through, and as we tip the brandy towards the flame, if it's hot enough, we should be able to get that flame coming on the brandy, take it over to the Christmas pudding, and just pour it over the top. And hopefully the camera's catching this, and we sing Christmas carols and serve this up. Merry Christmas. That is flaming your Christmas pudding on Christmas Day. And then you wake up and it's not even Christmas at all, and you've got to eat a Christmas pudding.
Anyway, can we rewatch it? Yes? Yeah.
Hi, and a big welcome to Steve's Kitchen. I've got the Christmas hat on again. One of my subscribers, or one of the viewers here, Bread Sandwich. Now, they had a different name earlier in the year. They've changed it to Bread Sandwich. Well, it's a great name. They asked me whether or not I could show them how to flame a Christmas pudding the way we do it at Christmas, and I promised for quite some time that I would do this. So I'm going to take one of last year's Christmas puddings, this beauty here, and I'm going to flame it. We're going to be taking some brandy. I'm going to be pouring a shot of brandy into a ladle, heating it up over a candle, and then we're pouring it over the pudding. Let me show you how it's done. Now picture this, if you will. It's Christmas Day. It's been beautiful. It isn't September. It isn't sunny outside. But it's actually Christmas Day. We've just had the family around. We've had the big Christmas turkey and the beautiful ham. And now everybody's feeling really overfull. And then you bring the Christmas pudding out. And everybody knows there's just enough space. So we get our brandy on the ladle. We've got a candle on the table. If you haven't got a candle, you can always do this over the gas stove. And we're just going to heat that brandy through. As the brandy heats through, and as we tip the brandy towards the flame, if it's hot enough, we should be able to get that flame coming on the brandy, take it over to the Christmas pudding, and just pour it over the top. And hopefully the camera's catching this, and we sing Christmas carols and serve this up. Merry Christmas. That is flaming your Christmas pudding on Christmas Day. And then you wake up and it's not even Christmas at all, and you've got to eat a Christmas pudding. Thank you for watching. It's been a lot of fun.
Okay, your homework is on the board. So the first one is only if you're doing the enriched stuff. Page 10 for everyone. You're going to read and do pages 53 to 56. This should be a little bit of review from last year. Chemical properties, physical properties, chemical changes, physical changes. We're not doing all of it, but we'll get through at least part of it. Make sure you read it, because it won't make sense if you don't read as well as try and answer the questions. And we will revisit Rutherford's model next day. Yeah, if you've done the enriched stuff or just have the enriched stuff, yeah, you can hand that in. I can use it next year.